All right, welcome to Who Controls the Network. So what am I talking about today? All right, so some organizations have two different teams, one that manages compute and one that manages the network. And sometimes these two teams don't always get along. If that's true of your organization, welcome to couples counseling. But I'm not a therapist, so I can't help with any emotional healing here. I'm just going to provide some technology-based solutions. So the root of this issue is that the division between the network and compute is a little bit blurred inside OpenStack. So let's take a look at an example. So you have these VLAN ranges, for example, that you can configure within Neutron. And so that's configured on your compute hardware by the compute team. But suddenly, through an ML2 driver, that gets propagated up onto your network. So how do we deal with that? OK, so we need to block any unwanted network config from showing up on the network from the compute. And we don't want the compute team to be scratching their heads when something doesn't work. So we need to provide a way to have feedback going back to, and assisting the compute team to provision the network in a mutually acceptable way. So as far as blocking mechanisms go, there are three different levels of head scratching, basically. So the first is when a failure basically doesn't result in any failure in the API, and it doesn't result in any failure in the logs. So you're going to be left scratching your head pretty vigorously. The second is when there's a failure in the log, but there's no API call failure. So you're going to check the logs, scratch your head while you're doing that, but eventually you'll find the issue in the logs somewhere. But finally, the best kind of failure is when the API call itself fails. You immediately know that something went wrong. Assistance is a little bit trickier. So the simplest form of assistance is for the compute team to ask the network team what they should put in their config files, and then they can go and put it in the config files. But then if the network team makes changes down the line, you're going to end up in this situation where you have to go back and forth to figure out what new config to put in the files. You're going to have to restart your services. It's going to be a whole mess. So automated assistance is a bit more work up front to set up. But in the long run, when the networking team goes and makes changes, the assistance mechanism becomes aware of those changes, and everything automatically adjusts so that the compute team doesn't need to actually make any changes on their end to support the new network config. So when implemented well, the network team configures their blocking mechanism, which prevents the compute team from messing with their precious network. And OpenStack detects that config changed and automatically switches to acceptable config in the compute side in the network, into the network. So when anything goes wrong, it's also immediately apparent. So that sounds good and all, but how does that work in practice? So I'll run through some examples here. So much of Neutron is developed in a modular fashion. So that means you can just switch out components, combine components in a lot of different ways. So two such components are ML2 drivers, which are responsible for configuring networking hardware, and type drivers, which are responsible for allocating VLANs, VNIs, and other identifiers to networks. So we can leverage the ML2 driver to reject any provisioning of unacceptable IDs for, via an ML2 plugin. And we can use a network type driver that automatically selects acceptable network identifiers via communication with either a network controller or a series of TORs. Using a non-default type driver is a little unconventional, so this is what that config looks like in the ml2.conf. In practice, what happens is the network notifies the type driver of the set of acceptable VLANs. So then when Neutron goes to create a network, it asks for a VLAN from the type driver. The type driver gives it an acceptable VLAN to the network team. So then Neutron will go and create a network with that VLAN. That goes on to the ML2 driver. And the ML2 driver eventually configures the network hardware. So we have this nice loop of feedback, all instigated by the network team's config. So what happens if the compute team gets naughty and decides to they want, say, VLAN 1, which is a management VLAN, but they're just trying to sneak into the network team's management VLAN, which the network team probably doesn't want. So they try to create a network with VLAN 1. The ML2 driver goes to the hardware and tries to provision VLAN 1 on the hardware. But the hardware is going to say, no, you can't do that. Failure. But so that the compute team's not just left scratching their head, what we're going to do is we're going to propagate that failure back to Neutron and fail that API call, say, no, you can't have that network with VLAN 1. So with IP allocation, you can do something similar, which is you block unwanted IP addresses using an external DHCP server that's under the control of the network team. And then you can ensure that acceptable VLANs are provisioned using an external IPAM. Unfortunately, the way that's set up today is you're not going to find that the failure happened if you try to provision an unwanted IP address unless you go dig through the logs. So a third example is with traffic control. So if the network team only wants certain types of traffic entering their network, they can configure ACLs on the TORs that will block traffic they don't want. And so that the compute team's aware that they've done something that the networking team doesn't want, what you can do is you can enable a Neutron plugin that will warn you when you apply a security group to a virtual port that's incompatible with the ACL that's existing on the top of rack switch. And that's all I have. Thanks for coming. Anybody have any questions? All right.